in the Radiologic Imaging Department is a practice that oversees that both a high technical quality of imaging is performed at the same time a high standard of service is delivered to patients. The practice ensures that the standards are regularly tested and the system as a whole is continuously improving in order to deliver the best quality healthcare with the utmost safety. The ultimate goal is a safe and efficiently run radiology department that consistently produces quality diagnostic images that will aid in providing an accurate and timely diagnosis and treatment of the patient while still adhering to safety measures, and includes every aspect of medical imaging technology from the safety of the room design, selection, care, maintenance, testing, support, and disposal of radiologic equipment to oversight of management informatics systems, patient care and scheduling, exam selection and procedure, patient respect and confidentiality, and staff development and management. There are a number of protocols regulated by various agencies to ensure specific industry standards are met. The Radiation Control and Safety Act was enacted by the federal government in 1968 as a means to oversee that specific government-mandated standards are met and includes the 1990 Safe Medical Devices Act and 1992's Mammography Quality Standards Act. These acts are reviewed and enforced by the Center for Devices and Radiological Health, a facet of the FDA which is overseen by HHS, the Department of Health and Human Services. This government agency regulates numerous federal programs that contribute to public health and wellness and include programs that are important in ensuring ethical care of patients, such as HIPAA. In addition to government agencies that regulate these healthcare and safety standards, there are various quality management accreditation agencies used by hospitals and medical facilities to regulate and elevate the standards of medical care, such as the Joint Commission, a U.S.-based nonprofit that accredits various U.S. healthcare organizations. The practice of quality management is subdivided into two main disciplines, quality control and quality assurance. Both are of utmost importance in medical radiation procedures and work in synergy to deliver safe, quality healthcare to patients. We will start by differentiating between the two. Quality assurance involves a systematic collection and evaluation of data to ensure excellence in healthcare based on specific indicators related to protocol and results. Factors that are analyzed for quality assurance include such things as repeat rates, pathology correlation, appropriation of exams utilized, adherence to patient care guidelines, staff and office management, and efficiency of the department. A successful quality assurance program involves the effort of the staff to ensure that diagnostic images obtained are of the highest quality possible, with the least radiation exposure and the lowest cost to the facility. Quality assurance is a broad term that is ever expanding to not only include working to maintain the highest levels of quality in patient care, but to consistently work to improve them. This philosophy is known as CQI, or Continued Quality Improvement. There are many protocols and measurement systems employed to ensure this. One method that is widely used in radiology departments and can easily be adapted to a multitude of medical settings is known as FOCUS PDCA. It is an acronym that outlines a methodology to target and remediate problems. Quality control refers to the regular intermittent technical testing of medical equipment and evaluation of image quality to ensure technical expectations are met. Quality control initiatives establish acceptable ranges and then maintain and improve on these set standards of what is acceptable in relation to technical aspects of radiologic imaging. They perform such tasks as routine monitoring of equipment parameters by acceptance testing and preventative maintenance, as well as establishing and implementing a protocol to take corrective action when these parameters are not met in order to rectify the issue. Included in this is the maintenance, repair, and testing of the facility where the equipment is being utilized. A number of trained professionals are involved in a successful quality control team. The following flowchart outlines the responsibilities and tasks associated with quality control. We will now outline routine tests that are performed as part of the quality control protocol for calibration and testing. We will examine what, how, and why they are performed and what is an acceptable result. KVP needs to be routinely checked as the actual values tend to change over time as a function of normal wear of the tube, resulting in damage to the tube itself and/or components such as the filaments, bearings, anode, etc. These changes, as well as other latent failures, can result in unpredictable output KVP production, which can yield unpredictable results manifested as unacceptable contrast and image receptor density and can ultimately result in repeated exposures. KVP accuracy is tested using a digital KV test meter or a computerized dosimeter. When various KVs are tested within the diagnostic range, the selected KVP and actual peak energy of the output beam should not differ by any more or less than 4% KV of the calibrated setting for general diagnostic equipment and not more or less than 5% KV of the calibrated setting for mammography equipment. If a discrepancy is detected, recalibration should be performed to correct it if possible, or otherwise repair or replacement of the tube may be necessary. Milliamperage levels also often change slightly over time as a result of the aging tube. Therefore, these levels also need to be routinely checked. Not only will a deviation affect receptor exposure levels and thus image quality, it is of utmost importance to safety as it is directly proportional to patient dose. Milliamperage refers to the current that is supplied to the cathode and when calculated with time produces the mass, which has a linear relationship to the X-ray intensity produced. Each milliamperage station should be evaluated using a penetrometer. The reciprocity law, as it relates to mass and is demonstrated in the photographic model, states that a reaction of a photogenic emulsion to light will be equal to the products of the intensity of the light and the time of the exposure. In simple terms, as long as mass is the same and all other variables remain constant, any combination of milliamperage multiplied by time can be used to produce the same quantity of radiation and therefore the same density. Linearity of milliamperage can be evaluated using this law, keeping in mind that the quality control protocol testing and calibration should be performed for KVP output as well as quality control testing on the timer first, to ensure that milliamperage testing is accurate, as any inconsistencies in KVP and time could lead to inaccurate results obtained in testing the mass. It should be also noted that inherent limitations with regard to instrument and equipment design will likely demonstrate some level of variation, although recent manufacturing improvements have minimalized this. In this way, linearity of mass can then be tested using a computerized dosimeter, with exposure changing in MA and time proportions yielding milliroentgen per mass measurements within 10% accuracy of one another. The following formula can be used to calculate the accepted level of linearity. The accuracy of the timer has a direct relationship with patient dose. As previously mentioned, the timer shares an inversely proportional linear relationship to milliamperage when mass remains constant. Remember, milliamperage times time duration equals mass. Therefore, in considering the testing and calibration of mass, the timer should be evaluated first. The most efficient way to test time is with a computerized dosimeter, and the measured value should be within 5% of the labeled setting. The following equation can help you calculate the percentage of timer error. When performing quality control testing of technical output of radiologic equipment, it is important to assess the accuracy of the data collected and that the equipment maintains consistency in that output from one exposure to another when using the same technical factors, and for this reason we need to know the amount of variation we get. To ensure this, we can calculate the coefficient of variation as follows. Only 1% of the energy used in the production of X-rays contributes to the useful beam. The rest is converted to thermal energy or heat, and this can damage the tube. For this reason, measures are taken to avoid overloading the tube. These protective measures and fail-safes should be tested regularly to prevent X-ray tube damage. One preventative measure that may be taken is proper warming up of the anode, as applying excessive heat to a cold anode too quickly may cause it to crack. Most equipment will employ an overload protection circuit to prevent things of this nature from happening. Testing should be performed after calibration of technical factors and should be repeated annually or more frequently if there is evidence or question of a malfunction of this feature. Half-value layer is defined as the thickness of an attenuating material at which the intensity of radiation will be decreased by 1/2. Half-value layer, or HVL testing, provides important adjunct information to KVP testing about beam penetrability and with respect to type of rectification, applied KV, and total filtration of the primary beam. Recall that total filtration is important for radiation protection as well as image quality by absorbing and thereby eliminating photons that are too low energy and will therefore not contribute to useful information hitting the receptor and only contribute to patient dose. When testing HVL, it's important to be able to evaluate for discrepancies. Generally, when the HVL value reduces, it is a result in less KV being applied to the tube. An increase, assuming that the applied KV value is accurate, may be evidence of extraneous reactions with particles in the tube, which may occur as a result of tube aging. The following chart represents half-value layers for specific KVP values. Testing the integrity of the focal spot size should be done regularly in order to yield expected results and maximize image detail, as the focal spot size can increase with normal aging of the equipment. There are various tools that have traditionally been integral in testing focal spots when using film. These include a pinhole camera, a slit camera, and a star pattern resolution device. Pinhole cameras test the measurement of the focal spot by creating an image of the effective focal spot. Recall that the effective focal spot in relation to the actual focal spot is dependent on the target angle of the anode and the size of the filament. The pinhole camera is not the first choice of tool to use and is reserved for focal spots larger than 1/3 of a millimeter because of its difficulty of use, and user error can lead to inaccuracy of results. In addition, pinhole cameras require excessive tube loading and the resulting heat can damage the tube. Slit cameras create two exposures, one measuring length of and one measuring the width of the focal spot. Inaccuracy is still an issue, though this method relieves the added insult of overloading the tube. Star test pattern devices are useful in measuring the focal spot size as a function of geometric blur and can aid in monitoring changes in the focal spot size. Traditional testing methods are difficult to employ. Results can be blurred at the edges, and obtained dimension results may be influenced by exposure technique. In addition, with the now widely used implementation of digital detectors, the limited magnification available combined with the reduced digital detector spatial resolution has resulted in even less accuracy using these methods. The newer digital systems and their inherent limitations with respect to detail have also created a need for smaller focal spots in order to achieve the desired detail. New quality control testing methods that respond better to CR radiography are being employed, such as using a coated aperture mask and digital detector. The results of this testing, when compared to traditional testing, have been promising. Integrity of beam alignment and collimation are extremely important, both in avoiding the practice of unnecessary radiation of tissues not being imaged and to reduce the likelihood of cutoff resulting in repeat imaging and therefore increasing exposure. There are multiple areas where discrepancy can exist that can lead to unexpected image results. They can occur with the collimator, or where the light field is not consistent or poorly calibrated with the beam, with the alignment of central ray and or with the alignment of the bucky, or with specified distance indicators resulting in inaccurate measurements of desired exposure as a function of distance. These factors may be tested simply using a tape measure and visual tests using congruence and perpendicularity tools to test the accuracy of the beam alignment with respect to the integrity of direction of the beam and accuracy of the collimated field. The example shown is an example of a penny test to check for light field alignment. Particular attention should be paid to the performance of the system while it is in the AEC mode, or under automatic exposure control, to ensure the safety of the patient image quality, and minimize repeat exposures. This is done by ensuring that the exposure reproducibility standards are met, ion chamber sensitivity is consistent when evaluated comparing them, exposure response is consistent with manufacturer guidelines, the backup timer is functioning properly, in case the exposure is not terminated properly by the AEC or if the technologist selects the wrong exam, and that the digital radiography detectors are functioning properly. In addition to ensuring that large radiographic equipment quality be tested regularly, it's important that radiographic accessories be maintained and routinely tested to improve patient and staff safety, improve image quality, and minimize the need for repeat exposures. Care should be taken to protect equipment and supplies and keep them clean to prolong the life of them as well as prevent the transmission of infection among patients and staff. IPs, PSPs, and cassettes should be kept clean, dry, and care should be taken to prevent physical damage that could affect their ability to be read through the scanner or cause artifacts in the image due to dust and scratches. They should also be routinely checked for artifacts that, if not realized, can present as radiologic findings on a patient's exam. Cassettes are constructed to protect the sensitive PSP plates contained within them. The cassettes should be held on their edges and stored vertically to prevent warping. Extreme temperatures and contact with fluids should also be avoided. It is important to keep in mind that a dirty cassette can itself become a contaminant to patients and staff. Grids should be handled carefully to reduce the incidence of the lead strips from moving and thereby causing artifacts in the image or misalignment with the central ray, leading to missing information, misinformation, or grid cutoff. This could result in an unacceptable image and necessitate a repeat exposure. Protective shields such as aprons and gloves should be cleaned regularly to prevent the spread of infection and stored properly as to not bend the material, as this can lead to cracks and thus increase exposure to the person utilizing them. As you can see, quality management in radiographic imaging is dependent on many things, and in order to be successful, relies on the teamwork of the radiology department as a whole and requires an ever-evolving approach to reach its goals of quality assurance, quality control, and continuous quality improvement in order to consistently elevate the standard of healthcare.